Okay, a couple of quick announcements. Don't forget that you have your exam next Thursday. So exam 1, I think it's March 11th, Thursday. And you will have, we will talk about the details of the exam in a little more on Tuesday, next Tuesday, but you will essentially get 1 hour and 15 minutes, 75 minutes. There are a couple of students who have registered with STRC, and they will, of course, get time and a half for the exam. And I will contact, if you are, let's put it this way, if you have registered with the STRC and need more time for exam, please reach out to me. What I'm gonna do is I'm gonna ask my grader to proctor the exam for you guys in a different room, in a conference room, right? So, and I'm gonna tell you where the conference room is, but it is in the same building, just in Wing A, just beside the main office for the mechanical engineering. And we will talk about the questions in detail, in more detail on Tuesday, but the exam is on Thursday, next Thursday. So in 9 days, essentially. This Thursday's class, which is going to be March 4th, right? Will be online. So what I'm going to do is I'm going to record the lecture, post it on YouTube, and then post a link to Blackboard, right? We won't have any live class because I have to be somewhere, but I will record everything. What I'm thinking of doing, it really depends on your preference, so let me know what you think, which one works better for you. And if you don't have any preference, I can just decide on my own. I was thinking of, instead of giving lecture on Thursday, just solve example problems for you that are going to be similar to your exam problem. Or I can do that on Tuesday and do the lecture as a recorded lecture. Whichever you prefer, doesn't really matter to me. If you have any preference here, I saw one person agreed with solving the example problems as a recorded lecture. If there's no one else who has any preference, I guess we'll just go with that. And I was planning to post a video for you in which I was going to solve the homework 2 problems and also the rest of the example problems for chapter 3. But I didn't have the time. I will get to post it during the weekend. So you will essentially get 2 recorded lectures in which I will solve the example problems. And then we will continue the lecture discussion on Tuesday, okay? As a live lecture. Okay, so exam, your homework 3 will be posted today. If not today, sometime tomorrow. And you will have until, I guess, Tuesday next week or Wednesday to submit your homeworks, essentially. And I will make sure to post the solutions to all of the homeworks before exam time. Is there any questions or concerns about the exam, about the online lecture we're going to have? Yes.
When you're going over the practice problems, can you also tell us kind of which ones might be on the exam, not necessarily the problems, but what topics will be on the exam?
I can definitely do that. That's no problem. But what I'm thinking is I will try to cover everything on the exam. So you will either get a very easy, multiple choice question from one of the topics that I can't give you a huge problem all of, right? So essentially, I will try to cover everything. Right? But what I'm thinking right now for the exam is to give you 10 multiple choice questions, which I ask you conceptual problems. You just choose or a true false or a descriptive question. I don't know, but the questions shouldn't take more than like 10 minutes, 15 minutes of your time, and then give you 4 problems, which will get harder as you progress through the exam. Right? So we'll start with easy problems and we move on. That's what I'm thinking right now, but I haven't designed the exam yet, so I will definitely let you know about it on Tuesday. Okay. Okay. So if there's no other questions, let's start the lecture. Today we are going to start talking about fluid kinematics, which is the topic of chapter 4 of the book. This is a more general approach to what we did in the previous chapter, which was the elementary analysis of the fluid dynamics. So we are going to focus on fluids in motion versus fluids at rest, which we did in the first 2 chapters. This will be the topic, the main topic of this chapter. And from this point on, it will always be the topic of our fluid dynamics analysis. So by the end of this chapter, you will hopefully know how to you'll understand what are streamlines, what are streak lines, what are path lines, and you will understand how to find the total acceleration using the total derivative, or how to find any total derivative of any properties in fluid mechanics. And you will also learn about the Reynolds transfer theorem. Something that you have to make sure you understand: Reynolds transfer theorem is a very mathematical concept, right? It has lots of integrals, and it is one of the harder concepts that we are going to learn in this class. So you just have to make sure you bear with me. You ask any questions you may have. You just study the material, right? And we'll solve a lot of example problems from the Reynolds transfer theory. And your exam will actually cover up to the Reynolds transfer theorem, so 3.5 chapters. Okay, so the material we're going to cover today will be a part of the exam. Okay, so let's begin. The first thing we want to talk about is how to describe a flow. Describe a flow. One of the most important parameters when it comes to fluids moving is the velocity of that fluid, right? Velocity is a vector that can have components in all directions in Cartesian coordinate system. Its components in the x direction is called u, component in the y direction is called v, and its component in the z direction is called w. So velocity itself, the main vector, can be a function of x, y, z, and time. It is true for all of its components as well. Same is true. So velocity component in the x direction can be a function of x, y, z, and t time. Same is true for velocity component in the y direction. And same is true for the velocity component in the z direction. Sometimes it gets a little confusing for students to understand how the velocity component in the x direction can be a function of y or z. That's actually, it's very easy to explain. Let's say this is your Cartesian coordinate system. This is your x, y, and z. Your velocity component in the x direction is this, u, right? Let's say your general velocity is this, its component in the x direction is going to be u, right? Capital V. Its component in the y direction is going to be v. Okay. If this velocity is going to be different in this location, this component of the u velocity. Let's say u velocity is 1 meters per second here. If this is 2 meters per second here, then your velocity, your x component of velocity has changed with respect to x and y, right? We have moved in the x direction and we have also moved in the y direction, right? So velocity, every component of velocity, it doesn't really matter which component it is, can change in a space and in time, okay? And this is the main parameter we're going to use to describe the flow field. Okay, the velocity itself is defined as the derivative of position vector with respect to time, and the magnitude of velocity is going to be equal to the square root of all of its components. Okay. Okay. Let's have an example to better understand this. Let's say we are given a velocity vector which is v naught divided by L. This is a constant multiplied by negative xi plus yj. Okay, and we want to find a location where the velocity, the magnitude of velocity is equal to this constant velocity v naught. Okay, how should we approach this problem? The first thing is that we need to find the magnitude of this velocity. What is the magnitude of this velocity? We define the magnitude of velocity as this square root. We don't have the third term. It's just a two-dimensional thing. Your u here is v naught divided by L multiplied by negative x, right? So v naught divided by L x squared plus your v here, a small v, is going to be v naught divided by L multiplied by y squared. Okay, and the idea was we want to find a location where this v naught with this magnitude of v is equals to v naught. So let's raise this whole thing to the power 2. I'm going to continue writing here. V naught squared is going to be equal to v naught squared divided by L squared multiplied by x squared plus y squared. This will cancel out. And then we're going to get x squared plus y squared equals to L squared. So this equation, if you recall from your basic mathematics, represents a circle with the radius L. So this tells us for this velocity field on a circle with radius L, your velocity is going to be equals to v naught. That's only the magnitude of velocity, though. The direction can change, right? Does it make sense? Okay, so on this circle, the magnitude of velocity is going to be equals to v naught. That's the first thing you need to understand, the velocity vector, when you want to describe a flow field. But the next step in describing a flow field is to understand different perspectives that are out there when it comes to flow field descriptions. So flow field descriptions. You want to learn a little bit more about what are the different perspectives. There are two main perspectives. First is Eulerian perspective, and the second one is Lagrangian perspective. Lagrangian perspective is when you sit on a particle of the flow and move with it, right? And then describe that movement of that specific particle, you are essentially using the Lagrangian perspective to describe a flow field. Okay, so sitting on a particle and then describing your flow field is the Lagrangian perspective. You're essentially moving with your flow. You're describing the movement of a flow. Think about it this way. They ask you to describe the flow movement of a river, right? The observer who is swimming in the river, his or her perspective is going to be different from the observer that is standing on the side of the river, right? From the flow field. So the swimmer's perspective will be the Lagrangian perspective. But the person who is standing on the side of the river is going to give you the Eulerian perspective. Okay. So when you're using the Eulerian perspective, you essentially have to prescribe all of the properties of the flow field, like pressure, temperature, velocity, and all of those things. And in most of our analysis here, we are going to use the Eulerian perspective. By Lagrangian perspective, you are going to analyze the interactions of fluid particles, right? And we are not talking about the fluid molecules. We are talking about these arbitrary small elements of the fluid that are moving, right? That we are going to call fluid particles. So we are mostly concerned with the Eulerian perspective, not the Lagrangian perspective. But you just have to know about the different perspectives that are out there. But the flow field itself can be the flow field itself can be a three-dimensional flow. It means that your velocity will be changing in all the three-dimensional, or we can have a one-dimensional, two-dimensional, or we can have a simpler types of flow. So that's another perspective. How your velocity is going to change as a function of space. What are the spatial changes of your flow field? Another approach is to look at how are the temporal changes of your flow field, or how does your flow field change with respect to time. So for the spatial changes, we're going to have one-dimensional, two-dimensional, and three-dimensional. That's it. But for temporal changes, time-dependent changes, the naming scheme is going to be a steady state, or a steady flow, or transient. which essentially means that your properties are either going to change with time, signifying the transient flow, or are not going to change with time, which is going to signify the steady flow, right? Not changing with time, and this one is changing with time. On a steady flow or transient flow is, of course, a little more difficult to analyze. Any questions so far? Okay. Let's see an example. I have also uploaded the lecture notes for this chapter already. And I don't know if you see this or not. Let me bring it down. So we have an example of a steady flow here on the left. Get this one. See, you don't see any changes. It is a movie, right? But you don't see any changes in the flow field. There's no obvious changes in the flow field. But when you add a disturbance to the flow, you see the changes, right? You see it is changing. The local properties are changing with time. Then you remove the obstacle, we will go back to the steady state condition. Again here, the changes with time. Okay. This one is from the planet Jupiter. You have the gaseous structure around it, right? And you see, you don't see it very obviously from here, but you can see the changes in the gas movement, the changes in the flow pattern on the planet. Yeah, it is more obvious here. Do you see the changes? Yep. See these changes? These are all signify a steady state, on a steady state, on a steady flow field. Okay. If these changes in the flow field are repeatable, right? The changes in the steady changes in the flow field, if they follow a trend, then we are within the laminar flow region, right? But it's just for introduction. You don't need to know anything about the laminar versus turbulent flow. But essentially, if the unsteady changes are based on a trend, if they follow a trend, we are in the laminar flow region. If not, meaning that if they don't follow a trend, we will be in the turbulent flow region. But that's all of the scope of the course. So just be aware that there is laminar versus turbulent flow regime. I will talk a little more about it later on. Okay, so we understand different types of the flow. We understand the two main perspectives of the flow. Then we are going to next step is to learn some mathematical and physical tools, learn about those tools that will help us describe a flow a little better. I think we are somewhat familiar with streamlines. We talked a little bit about the streamlines in the previous chapter. Streamlines are a very handy tool when it comes to the analysis of the flow. But we also have our flow visualization. We also have a streak lines when it comes to flow visualization, and as well as the path line. We define the streamlines as the lines that are tangent to the velocity vector. always, this is the definition. So they are always tangent to the velocity vector. Okay. So let's say this is a streamline. The velocity vector is always tangent to it. Okay. And right now, we want to find the equation of this line, which essentially means that we want to find the slope of the line at each location. And if you are in a Cartesian coordinate system, two-dimensional, the slope of this line is going to be the derivative of y with respect to x, right? So essentially, the equation of the line for a streamline can be calculated by using the derivative, finding the derivative of y with respect to x. Well, how can we find that? Look at this equation. You have your theta here, right? The angle it makes with the y-axis, essentially, right? This is both true for the velocity vector, same angle, and the line that signifies dy or dx, right? The slope of your line. dy over dx is equals to tangent of this theta, right? And we can also find the tangent of this theta using the velocity vector, right? Your velocity component here is going to be v, and it's going to be u here. So we're going to get v divided by u, right? That was the definition. So if you have the velocity vector, you should be able to find the equation of the streamline. Velocity component in the y direction for a two-dimensional case. Velocity component in the y direction, velocity component in the u direction. If you just divide the two, you will be able to find the equation for a streamline. Okay, and you have already seen how useful a streamline can be. We essentially derived the whole Bernoulli's equation along a streamline, right? So if it wasn't for this tool, we couldn't have had the Bernoulli's equation, which is a very handy equation when it comes to fluid mechanics analysis or fluid dynamics analysis. So let's solve another example to see if we can find how can we find the streamline equation with having the velocity vector. This time we are going to have the same velocity vector as we did previously. So v naught over L, two constants, negative xi divided by yj. The goal here is to find the equation of the streamline dy dx, right? We said it is equal to y divided by u. So what is v here, or v divided by u? We have v naught divided by L, y divided by v naught divided by L, negative x. So these two cancel out. And dy dx is going to be equal to y divided by negative x. So we have the slope of the streamline. Okay. Well, how can we find the equation of the line itself? We have the slope of the line. We want to find the equation for the streamline. Essentially, we want to plug in any x and find the corresponding y for that specific on that streamline. Okay. Pretty simple. Just have to take the integral. Move things around. We're going to get move y here and x the x to the other side. We're going to get dy divided by y is equal to dx divided by x. And then you can take the integral from both sides. What is the solution to this integral? What is the integral of dy divided by y? Does anyone remember? Natural log of y, exactly. So your natural log of y is going to be equal to negative natural log of x. Since this is an indeterminate integral, just have to add a constant value to it. Okay, so this is the general equation for the streamlines for this velocity field. Okay, if we were told that to find the equation of a streamline, that a specific streamline that passes through 1 and 1, right? X equals to 1, y equals to 1. The only thing you really needed to do to plug 1 here, to plug 1 here, and then you could have find C, right? What would be C for that case? What would be the equation of line for that specific case? X equals to 1, equation of a streamline that passes through this point, this specific point. What is the natural log of 1? 0, right? So you're going to get 0 here, 0 here. Your C would be 0. So the equation of this specific streamline that passes through this one is going to be natural log of y is equals to negative natural log of x. Okay, so this is for the streamlines. And let me see. Yep. The next tool that we have to become familiar with is the streak line. A streak line is something that is mostly used in experimental analysis for flow visualization, right? Whereas the streamlines are mostly used for like analytical solutions. So what are streak lines? Streak lines are the combination of all of the points, all of the fluid particles that pass through one point, right? So let's say this is the point that I'm focused on. One fluid particle passes through it at time 0, right? Let's say at time 1 second. Then there was another fluid particle that has already passed through it at 0.9 seconds, right? Before this particle is passed. There was another particle that has passed through this specific point in the fluid at 0.8 seconds. And we will have another one that has passed through it earlier, and so on and so forth, right? A streak line is going to be the line that is going to connect all of the points that have already, all of the particles that have already passed a specific point. Okay, does this make sense? Okay. And a path line is defined as a path that the particle has moved or has traveled through a time, sometime. Let's say time t. So at time t equals to 0, your one particle was here, and then moves to this location at time equals to 1 second. So path lines are mostly focused on one particle, movement of one particle. Streak lines are mostly focused on the particles that have already passed through one point, right? One point in the fluid. Is there any questions? No. Okay. So let's move on and solve an example. This example is a little harder, if you will. So make sure you follow as we go, as we progress. This example is giving us a velocity field. This is the velocity field, v equals to mu naught, that's a constant, sine of omega t minus y divided by v naught I. So this whole thing is going to be your velocity in the x direction. This whole thing is going to be u, which is already a function of time and y, right? Plus v naught j. And this is going to be your v. And v does not change with time or x or y or z. V is just a constant value, v naught. It can be 1, 2, 3, 4, 5, whatever. That's a constant value. And we are asked to find the streamline that passes through the origin. X equals to origin is x0 and y0 at time 0. Okay, that's the first step. How can we find this streamline? We go back to the equation of the streamline we had. dy dx is equals to v divided by u. Right? What is the v here? V is only v naught, and your u is u naught sine of omega t minus y divided by v naught. Okay, that's it. And we have v, we have u, and this is equals to dy dx. Then you just move things around a bit. We are gonna get u naught sine of omega t minus 1 minus v naught dy is equals to v naught dx. Okay. What is the next step here? The next step is, of course, to take the integral. But you're going to get out of the integral here. The sine of omega t minus y divided by v naught is going to be, u naught is going to be there. Then we're going to get omega divided by v naught multiplied by cosine of omega t minus v naught. Right? And actually, that is v naught divided by omega. And on the other side, you're only going to get v naught x. Is this clear? Is how we took the integral clear? This is essentially the integral of sine of a constant. So what we did here was we took the integral of sine of a constant minus another constant dy dy. This integral is going to be 1 over b cosine of a minus by. Okay, the solution to that integral. Okay, so to find the equation of the line, let's have to play with this a little bit. Let's have to move things around. This is an indeterminate integral again. To find the constant of the integral, we say that it is going to pass through the origin. Then your time is 0, while we are passing through the origin, so x and y are going to be 0. Time 0, y 0, cosine of 0 is going to be 1, right? And v naught multiplied by 0 is going to be 0. So your c is going to be equal to mu naught v naught divided by omega. Plug that in. Let's substitute c for u naught v naught omega. You're going to get the equation of the streamline. Okay. Is there any questions here? Okay. Next part of the question is part B, is asking us to find the path line of a particle that was at the origin at time 0. So path line, we said the path line was the line that a single particle takes to go from point A to point E, right? You want to find the path line of a particle that at time 0 was at this location, x0, that a specific particle. How that one has moved, okay? Essentially, to understand that, we have to first identify how the location of that specific particle is going to change over time, right? We have u and v. V is your v naught. U is u naught sine of omega t minus y divided by v naught. Okay. Again, you want to find how the location of the particle changes with respect to time. Okay. And we have the velocity components. But what are these velocity components? These velocity components are the changes in location of a single particle with respect to time. So we already have this. You already have the changes of that particle's x component of the location with respect to time, which is that equation, and the changes in the y component of that specific particle's location with respect to time. So to find how the path line or how that particle moves over time, we only need to take the integral. For the second one, I'm just going to move dt to the other side. This is v naught dt. Take the integral. Your y, it is an indeterminate integral again. Your y is going to be equal to v naught t plus c. Okay? Let's call this c1. But we already have one piece of information that is going to give us some clue about the constant. That at t equals to 0, your y was already 0. So plug t0 here, y is going to be 0. So your c1 here is going to be 0. So we already know and understand the y component of how the y component of the location changes for that specific particle that has passed through the origin at time 0 with time, right? You already understand that. For the next part, we have to take the integral of this. This is dx is u infinity sine of omega t minus y dt. What is the solution to this integral? The solution to this integral keep in mind that y here is also a function of, let me actually do that. So it is a harder integral to take. So if you have something like this on a homework or an exam, you just have to keep that in mind, right? We have a y here, right? And we already know y is a function of time. So we have to take care of that. But we already know the function. That's v naught t, right? Let's plug that in. That's v naught t plus a constant, but we have already determined the constant. If we hadn't determined the constant, we had to plug the v naught t as well. Let's actually say that we don't know what the constant is. Let's plug the whole thing in. So we are going to substitute y with its function of time, whatever that is. Omega t minus v naught t divided by v naught minus is going to be c naught divided by v naught, right? So I just substituted y with v naught t plus c1, that divided it by v naught, and then, okay. So what do we have here? These two cancel out, will cancel out. We're going to get t minus t, which is going to be 0. So this whole thing is going to be equals to sine of omega c1 negative v naught dt. All of this is a constant that is not a function of time. So taking the integral is going to be very easy. Your x is going to be u infinity sine of negative omega c1 divided by v naught t plus another constant for the integral. Again, we are told that time t0, x is 0. So this whole thing is going to be 0. And your c2 is 0. So we're going to have the equation for that specific path line. x0, that eventually your final equation is going to be for the path line of the particle that was at the origin at time 0. Your final equation will be y equals to v naught t and x equals to 0, right? Because this c is already 0, and we determine this c2. This c1 is already 0. This c2, we determine that this should be 0. But what if we were told that at time 0 or at time whatever, we were at a different location? Everything would have been the same. The only difference would have been how we determine C1 and C2, right? Just plug the values in, you get new values for C1 and C2. Okay, is there any questions so far? No. So let's move on. And this specific, I forgot to mention this, this specific equation, this specific velocity field equation, it's an oscillating sprinkler's head. That's the equation for the velocity field of an oscillating sprinkler head. And let's actually see these as well and then move on. Just want to show you So these are going to show you streamlines or how the streamlines are visualized in an experimental setup. We have three circular things, right? And the flow is coming in from here. So these lines are tangential to your velocity. That's the definition of a streamline. You can see the formation of a streamline. You can see the, not very well, but you can see the stagnation point here. Again, another set of streamlines that are passing through some airfoils. A stagnation point is obvious here, where the velocity is 0. And then the next one is going to give us the streak lines. See, look at this point. This is the point. We are looking at the fluid particles that are passing through this point over time. You see the particles are moving. It's a little harder to visualize a streak line in an experimental setting. Okay, and the next one is going to be the path lines. A path that a particle moves. Like you can see the particles are, it's a little hard to follow, but this particle is moving in all of the directions. The next tool we need to understand, we need to talk about is the acceleration field. If you recall, we actually, for Bernoulli's equation calculations, what we did was that we talked about the second Newton's second law, right? So acceleration and how we understand acceleration is a very important part of fluid mechanics. Okay. If you recall from the Newton's second law, we had F equals to NA, right? That was the idea of the Newton's second law. So we have to have an understanding of how to calculate the acceleration. Okay. Okay. We usually define acceleration as a derivative of your velocity vector with respect to time, right? Your velocity vector itself is a function of x, y, z, and t. So if you recall from your mathematics, based on the chain rule or the chain rule of differentiation, how can we calculate this acceleration? This acceleration can be changes of v with respect to t plus, okay, changes of v with respect to x multiplied by changes of x with respect to t plus changes of v with respect to y, changes of y with respect to t with respect to t, yep, and changes of v with respect to z plus, multiplied by changes of z with respect to t. Okay, the chain rule of differentiation. Your velocity is a function of x, y, and z and t, and we want to take the derivative of something that is already a function of all these parameters with respect to only one of those parameters, with respect to time. So from your mathematics, this would be the correct representation of how we should find acceleration, right? Take the derivative with respect to time, then take the derivative with respect to all of the spatial coordinates, right? And then present the derivative of that specific spatial coordinate with respect to time. Okay? So this type of taking the derivative is actually called the total derivative. It is also called material derivative. There are different names for it, or substantive derivatives. But we are mostly going to use the material derivative and total derivative, and we use capital D for it. So your acceleration is capital dV, capital dt. Again, how can we find this acceleration? Take the derivative of v with respect to t plus derivative of v with respect to x, that's partial, plus multiplied by whatever we have done here. So this is called the total derivative, material derivative. It's a little different from what you have seen before, of course, because we usually what we did was just took the derivative of velocity with respect to time, right? And then we had the acceleration. But we are extending that understanding of acceleration, okay, to a total derivative. Okay. So let me repeat that. We have dv dt plus not partial, then partial v, partial x. We can replace partial x, partial t with the velocity component in the x direction. Right? That's the definition of velocity component in the x direction. Then partial v, partial y, velocity component in the y direction. Then partial v, partial z, velocity component in the z direction, right? So this will be the material derivative of velocity with respect to time, and this is how we calculate acceleration in fluid mechanics. And of course, acceleration itself is a vector. To find that vector acceleration, again, the x direction is going to be partial u instead of partial v, partial t plus partial u, partial x multiplied by u, partial u, partial y multiplied by v, partial u, partial z multiplied by w. And get the same for the rest of the components. So we're going to get partial v, partial t plus partial v, partial x multiplied by u, partial y multiplied by v, and so on and so forth. So essentially what this means is that I said this capital D, capital DT is called the total or material derivative. Whenever you see this type of notation, this is what you need to do. Whatever parameter you have inside, you take the derivative of that with respect to time. That's the first step. Then you multiply your x component velocity by the derivative of that specific parameter with respect to x. You do the same for the rest of the coordinates, the rest of the axes. Again, total derivative or material derivative. For example, if you were to take the total derivative of temperature, it would have been partial T, partial temperature, partial T, plus U, partial T, partial X, plus V, partial T, partial Y, plus W, partial T, partial Z. Well, what does this signify? We can, of course, we can divide it to two different sections. One will be the time derivative, partial V, partial T, or partial anything, partial T, and the other one, the spatial derivative multiplied by the velocity. All of these are going to represent the changes over time. The first one is called the local derivative. Local derivative. Which essentially talks about the changes of the property of a fluid particle when time passes, right, at the same location. To understand this part better, think about it this way. Let's say we are all here, inside here, and the changes of temperature over time is going to happen to us. I mean, we are going to feel the temperature change if they turn off the AC, right? The temperature, I assume, is going to, because there are a lot of us in here, is going to rise a little bit, depending on the time of the year, right? But we are not moving. We are just staying here. So that will be your local derivative. My body's temperature is going to change locally, right, if you turn off the AC. But the second part is called the convective derivative, term, or convective derivative. This part talks about the changes that my body is going, changes in temperature that my body is going to feel if I move from the location that I'm standing here to outside, right? Temperature outside is different from the temperature inside, right? So my body, the temperature I'm feeling is going to change, right? In both of these conditions, time is going to pass, right? Me moving outside, it will take time, right? And us turning off the AC, it will take time for my body to feel the temperature change. So changes in time has a local component and a convective component. If you are moving, if your particle velocity is moving and its velocity is changing as it moves, then you will have the convective derivative. If it's staying at the same location and its velocity or whatever is changing, then we will only have the local derivative. We can have the combination of the two as well, right? We can turn off the AC. I can also move from, at the same time, I can move from inside this room to outside of the building, right? Both of these will be present. Both the local and convective derivatives will be present. Okay. Is there any questions? Okay, so let's have an example, and then we can stop here. This example is giving us a velocity field. This is an incompressible inviscid fluid flow that steadily passes a tennis ball with the radius r. Steadily is telling us there is no changes with respect to time, right? Steady state. A steady state, okay? And this is the velocity field. V is u of xi plus, I'm sorry, no. U of xi, which is equals to v naught 1 plus r to the third divided by x to the third I. So it's just one-dimensional velocity, one-dimensional velocity field And R here is the radius of the tennis ball. X is the location in the X direction, right? We want to determine the acceleration of a fluid particle in this flow field. So let's try to find the equation. This part of the equation is 0 because the flow is passing the tennis ball steadily, steady state conditions. Velocity in the V direction is 0. Velocity in the W direction is also 0. So your acceleration is only going to be equal to U partial X. Okay? I'm going to write it down here. U partial X. So what is the derivative of this with respect to X? Anyone? Derivative of this term with respect to X. No one? Okay. So derivative of the first part, V naught by 1 is 0 with respect to X, it's constant. Then we have R to the third divided by X to the third, right? We are essentially going to take the derivative of a constant multiplied by 1 divided by X to the third, or we want to take the derivative of X to the raised to the negative 3, right? When you're taking a derivative of a polynomial, right, you have the power, you have to reduce the power, you have to decrease, subtract the power by 1. So negative 3 minus 1, you're going to get negative 4. And then you have to multiply it by a 4, essentially 1 over your power. So this derivative of U with respect to X is a derivative of V naught 1 plus R third to the X third, which is equal to the derivative with respect to X, equal to the derivative of V naught with respect to X, 0, and derivative of R to the third. You can take R to the third out of this derivative, and you're going to get negative 4 R to the third 1 over X to the fourth. Okay. Or negative 3. I'm sorry. What is this? Negative 2. Okay. So we have that part. Then you multiply it by the velocity you already have, this velocity field, to get the acceleration. And you will have your formula for the acceleration of a particle of a fluid in this flow field. Okay, so that's it for today. And there won't be any face-to-face classes on Thursday. I will upload the lecture. I guess we decided to upload the exam review lecture on Thursday, right? So I will review the exam material. Up until this point, everything will be a part of the exam. And then we'll continue this part of the lecture on Tuesday. I will also, we can talk about the exam on Tuesday for a couple of minutes, but that will be it. We won't talk more about the exam on Tuesday, unless you want to do the exam review on Tuesday and do the lecture on for the online class. But yeah, that's it. And have a good day. We have one question. Will there be an online option? No, there is no online option for the exam. You have to come to class.